Good afternoon, everyone. Today I'm going to talk about the development of an automatic classification system for the cetaceans using their vocalizations. So I see this problem as a problem of designing a speech recognition system or a Siri for the underwater, which has a decent language model. That means, it can distinguish between different whale species based on the vocalization audio that you give to the system, but we really miss the lexical models. That is, we don't know what they're talking about. So today I'm just going to talk about how to develop that language model. As a part of my undergrad, I spent a lot of time studying underwater acoustic sound sources, and that's me with the headphones. And being at MBARI was even special to me because I get to work on acoustics here. And probably this image, this looks like a selfie to me, taken by the hydrophone on the left side. That's the underwater mic. And you can see the Mars Observatory at the back. It's that's an observatory that is deployed 900 meter depth and almost 20 miles out from here. And the capability of recording almost real-time data and being able to analyze that as it comes, it's pretty amazing. But a more global problem that should be motivating us all is that these animals, they're disappearing, and it's mostly because of us. And this is just one instance showing that. And so I want to build a system, a reliable system that can monitor these animals in a better way using their acoustics, and probably prevent such things from happening. So now I will present my lady, Aquatic Siri. So you can see cetaceans, doing their daily business vocalizing, and here we kind of stick in a hydrophone, and so that we can listen to them, and we plug it into what I call as the Aquatic Siri. So she's supposed to make all these decisions, based on what she's hearing. So let's see what she does. Nice sound. So now you can see as a signal hits, the hydrophone, she runs all these algorithms within her brain, which makes a decision, whether it's a humpback whale, fin whale, blue whale, etc. And well, right now she's working really, really well. So now I want to tell you about the big picture, what's actually going on out there. So you can see you have the hydrophone, cetaceans vocalizing, and you have the Mars Observatory, and it has a wired connection back to MBARI, which is really impressive. And that is actually one of the signals that was recorded on the 31st of July. And you can see some of the cetaceans vocalizing, probably cetaceans vocalizing on the left. Then you can see some noise, and then you can see another sound source that is hopefully a cetacean that is vocalizing. And these files are huge. They're like 0.5 gigabytes. They're huge files, and it is very impractical to actually use these files for your processing. So what do? We kind of just what we do is we just pick out the cetacean calls rather than just taking the whole signal and just throw out all the other noise. And once we have these signals separated, as to distinguish between any two objects, you need certain features, certain common features to do that. So we calculate some acoustic features of these signals and then supply them to the classifier, and based on which the classifier makes a decision whether it's a porpoise, a blue whale, or sperm whale, etc. Now, let's talk about what I'm actually trying to classify, the species I really have. So when I came at MBARI, I didn't have the hydrophone deployed at Mars. And so we just went about using the Scripps dataset, and the 5 species that I extracted from, I extracted 5 species from that dataset. And right now I have 2 mysticetes that are, right now it's the blue whale and the fin whale. Mysticetes are the whales which vocalize at very low frequencies, up to 50 hertz. And on the other side, you have the odontocetes. They are the whales which vocalize at very high frequencies, ranging from 25 kilohertz to up to 160 kilohertz. So on this side, I have the curious beaked whale, sperm whale, and one of the porpoise. So I'm just gonna play, one of both the categories for your reference, so you see how they are. Yeah, it sounds like my stomach when I'm hungry. This is very ugly. This one is more interesting because these are high frequency clicks up to 10 kilohertz, and this is one of the curious beaked whale, and you can see the clicks. You can hear the clicks. Beautiful. Okay. So now let's talk about the features, the features based on which we are doing the classifications. So right now you can see 7 features. Each feature has different parts. So in total I have 34 features. I've selected both time domain and frequency domain features because in total, they give a, kind of a complete story about the signal rather than just, revealing half the information. So, considering, both the features, it's really helpful for us. So we'll see how that helps, in the results section. So now, how do you extract these features? So features are basically just mathematical formulas. And one way to calculate them, could be to just, pick up this audio signal and just push it inside the formula and, get a number out of there. But what I do is I kind of pick up this audio window of 50 milliseconds and I kind of run this over the whole signal, just by sliding it. And if you see clearly, there's an overlap with the previous, previous window. The way it helps is that, it kind of preserves the information that is stored within these small audio frames. It increases the resolution of your data. As you can see, there's almost noise here, and then you hear this vocalization, and that is, reflected in this is the energy, feature, and you can see how that is actually reflected in the values. I do both, do this on both the spectrogram, that gives you the frequency on y-axis versus the time, and I do the same on the time domain signal. So, both I get both the features. Now, finally talking about the classifiers. So nowadays in the problem of machine learning, you have a huge pool of classifiers already, and it becomes really difficult to select what classifier to choose for your application. So, well, I just went with a simple technique of choosing 2 very different classifiers. Yeah, this one is not getting things right, but still. So, the 2 classifiers that I chose were support vector machines. Support vector machines is a very chill classifier. It works really well. It works really fast. And if it works, amazing. But if it fails, it just fails. So here I've showed a 2D plane where you can see, the features are plotted for 2 different species, and the SCM basically tries to, find this plane between those 2 species, and kind of an optimum plane which can, separate those species in a, efficient way. On the other hand, I have the random forest classifier. They are very complicated. They think very complicated, and they take more time to run, but, they work really well in situations of where the classification problem is really difficult to solve. We'll see how both perform in the results section. Now going to the classifier testing, how do I actually test these classifiers? So I have this audio data, and what I do is I kind of clip the audio data into 2 parts. One is the test data, and the other is the training data. So like humans, we need experience, to make decisions in the future. In the same form, or the same form, we need training data, that is to be supplied to these classifiers so that they can gain experience, and based on which they work on the test data to make some predictions. Once that is done, we kind of calculate these graphs that you see on the right side and some metrics such as accuracy and precision, based on which you compare different classifiers. Before going into the results section, I just want to show you what I have, the data I have. So on the y-axis, you can see the number of calls I have for each species. So initially what happened was we thought that, the classifier is working fine, and, but there might be a problem of overfitting. So, the data might be just, the classifier might be just, overfitting the data, and it just might be performing well, and it might be fallacious. So what we did was we needed more data, but we didn't have any, database other than the Scripps data set. So what we did was we just created our own data, and using the same, the actual data we had. So what we did was we just kind of superimposed the noise from different hydrophone recordings, from the Scripps recordings, and we kind of superimposed them on the actual call recordings, and we created almost double data, and we'll see how that actually helps. So I guess this is the most interesting part of the presentation, are the results. So right now I'm classifying 4 species using both the classifiers. I'm still, the sperm whale is, I'm still working with the sperm whales right now. So you can see the accuracy of the random forest classifier is a bit greater than the support vector machines. And honestly, when I came, I thought getting anything above 88%, 89% would be just amazing. And getting an accuracy of 93.2%, and it just blew my mind too. And more importantly, I want to discuss about the ROC curves. So basically, on the y-axis, they give you the rate at which your classifier succeeds versus the rate at which your classifier has failed. So ideally, what you want is a higher true positive rate and a lower false positive rate. So ideally, these graphs should follow the the left edges, and the further they are from the dotted line, the better it is. So, and greater the area under the curve. And you can see for curious beaked whale and one of the porpoises, these areas are almost equal to 1. That means they've classified both these species almost perfectly. Though these are averaged graphs, so it must be around 0.995, but that doesn't make a difference. Now, so the classifier has actually performed really well. Now, to show you, what actually the artificial data does to your classifier. You can see here how the accuracy has actually improved by adding the artificial data. And more importantly, I want to talk about the learning curves. So you can see here, this is a learning curve of the training data. As the number of samples, as the number of calls increase in the classifier, how the training data, learning curve changes, and this is the learning curve of the test data. And ideally, they should kind of meet at a point, or they should be near to each other. So higher, the greater they are apart, the more the variance in your data set, and that's bad for your system. So, and you can see when I've doubled the number of samples, this gap has actually reduced. And I was expecting this, but I didn't think I would get this, but when I got this, I was like really excited. I was just jumping here and there. So this shows that the artificial data can be really useful. Finally, I just want to talk about one of the future works. One of the immediate future works we want to work on is something called as the soundscape. Soundscape is kind of the thing where you want to listen to everything that's out there, and you want to identify everything that's out there. And you never know, you might find something new. And before I jump into the ocean, try to find Godzilla or the Loch Ness Monster, I want to use my classifiers to kind of identify all these whale species and kind of estimate their population densities in this region. And not only this, but I want to study the seasonal variability of the vocalization calls, because these vocalizations kind of change with seasons. So if my system can actually adapt to these changes, the classifier can actually work, year long. You can just keep, running the classifier, and that would be just amazing. That would be like a holy grail for bioacoustics. Thank you, and I want to thank MBARI, the Packet Foundation for giving us this opportunity. I want to thank George, Linda for this amazing internship program, Danelle and John for showing me both the science and the engineering side of the project, Paul McGill for showing me the enthusiasm with all those audio files, the Rachel Carson crew for actually going and deploying the hydrophone so that we can get all these data, MBARI interns for making my stay in the US, my first visit in the US, one of the most memorable ones, and of course, I wouldn't be here without them. Without the cetaceans. So thanks to the cetaceans out there for your calls, for vocalizing. Any questions?
We have time for a couple questions. Go ahead.
Can you tell us a little bit more about the features that you extracted and how big they are? How do you normalize them across the data set?
So I have 34 features. And so as these features are actually calculated over 50 millisecond windows, so your final feature vector is like 34 features versus the time windows. Now, as the classifiers don't take an input of a 2D feature vector, so you need to kind of reduce the dimensionality. Either using, I actually used two techniques. One was just simple averaging, over different windows, and second is the principal component analysis by picking out the first component first component of the when you perform the singular value decomposition, the first principal component that you get. Some of the features, like most of the features, are based on the frequency. One of the features called as the melt frequency separation coefficient. That's the most, and I guess it's one of the most important features because it really tries to simulate, how our ear, kind of separates those frequencies. And if your ear can do that, we can kind of simulate that. MFCC is kind of a simulation of that, and that's why I feel it's just working pretty well with the, because of the implication of the MFCC features. I think does that answer your question? Okay. Yes.
Yeah. So separating out the different species is probably easier than separating out the individuals from the same species. Have you thought a little bit about that?
So obviously with one hydrophone, it is difficult to tell whether it's the same whale or if it's a different whale. That is possible. I mean, if you want to track different whales, different individuals, you need to have multiple hydrophones so that you can get different signals, and then you can then you can actually separate them. That was actually one of my projects when I was working at McGill last year, to separate different, if you have, like, say you have two cars outside, so how do you actually tell they're like different horns or different people talking? So you will need more hydrophones, or if they're vocalizing in different time frames. Well, if they're vocalizing in the same time duration, it is still possible to do it with one hydrophone. Yeah.
Given multiple hydrophones like that, couldn't you also figure out how far away they were from?
Oh yeah, sure. I would say, if I was working for hydrophones, I could find the exact XYZ location of these whales from the Mars observatory in real time and track them. We just have one hydrophone right now. when I'll be back in Bari working, I'll get 4 hydrophones.